This conference will now be recorded.
Okay, I'll go ahead and begin. Good morning, early morning for some of you, good afternoon, or good evening. My name is Steve Greb, the past director of GEOAquaWatch. Um, I'm going to do a brief introduction followed by our three speakers this morning. Um, and we'll have time for some questions after each of them speak. But we'll have to be brief because we have a lot of ground to cover. Um, Back in 2020, Geo partnered with the Google Earth folks to promote and advocate the use of Google Earth Engine in Earth observations and analysis. And they did a call.
Analysis. You did a call.
I'm going to ask
I'm going to
everyone to
ask
please mute
everyone to
their mic.
please mute their mic.
Thank you. As I was saying, they did a call of which we received one of their awards. There was no funding included with it, um, but they did um, have free commercial license, free training, and technical support, which was a big help to us. So this was essentially a best effort. The goal of the project was to provide a global scale, open access, and freely available, fit for purpose weekly water quality information for both coastal and inland waters to be used by multiple end users, including the science community, water quality managers, industry, and the general public. Of course, there's a lot in that goal. I think we might have been a bit naive when we drafted this. But moving forward, we had formed an algorithm team and kind of settled on the solid model, which was actually a suite of different algorithms. And so today we're going to talk a little bit about the progress that's been made with that work. And along the way, as we've been working on this, we've, I guess, gotten interest from other folks in the community, and our group has somewhat expanded. And so today we want to talk about not just what we're doing, but our future, and also find out what some of you other folks are doing. Um, so today we have three speakers. We're going to start um, with Nate Merrill from EPA, followed by Benjamin Page from USGS and Kelly Lewis from NASA. So at this point, I'm going to hand it over to Nate.
Hi, everybody. Thank you for tuning in from wherever you are. I'm coming to you from Narragansett, Rhode Island in the United States, and excited to share this work with you. I am giving sort of the big picture. Steve gave an introduction, and I'm going to motivate the need for Earth Engine for aquatic remote sensing, and then turn it over or talk about some highlights of the solid model implementation, which was the first water quality algorithm that we've chosen to collaborate and work on together to port into an Earth Engine environment. And then followed by Benjamin Page talking through some of his atmospheric correction work, and Kelly Lewis on adapting Ben's code from the JavaScript environment to the Python one, and applying it to Midwest glacial lakes. And lastly, a community discussion. So as Steve mentioned, this is a collaboration of the willing from multiple organizations. We've met monthly, kind of, and we're working through a collaborative GitHub project to build these water quality algorithms in Earth Engine, starting with solid. We had an initial goal of porting Acolyte as an atmospheric correction into the Earth Engine environment. I think Ben and Kelly can talk about some of the difficulties there and directions we went. It went in different directions right now. And this also came with some support time from the Google staff to get us up to speed on options, depending on the constraints we were working on and what we had scoped out originally. And I think through this show, you'll sort of see the progress we've made, the stumbling blocks we've hit and are currently working through, and sort of the directions that sent us in trying to put these types of water quality processes in this cloud computing environment. All the good things that come with that in terms of scalability, shareability, and some of the bad things like hitting paywalls, dealing with porting custom models and things like that. So big picture need for Earth Engine for aquatic remote sensing. Getting the data scripts, the data itself, and the computational resources all in the same place has a big advantages towards sharing it with other people, repeating it, and being able to take what you've done and apply it to a much bigger region without recreating a computation environment every time. It allows for collaboration with other disciplines. So I work at US EPA as an environmental economist, so I'm an end user for this stuff. And many of the water quality algorithms that seem to fit the bill for a study we're working on. For example, we're working on perceptions of clarity in coastal waters, and we were hoping to connect it with a coastal clarity algorithm. They are sort of stuck in journal articles, or maybe you get code for them, but you have to spin up a whole computing environment in order to make a production version that you could use. So these sort of cloud environments like Earth Engine, and there's others now like Sentinel Hub and Microsoft's Planetary Computer, put it all together and take away some of those upfront costs. So at least from how it's gone at EPA, the old way we did this was, big downloads, process imagery locally, do some of the pre-processing work on our side on, local computers through a whole amalgamation of softwares that sort of hand off to each other, not cleanly. And we lost we spend most of the time trying to get the data together with the computation, and we have less time to do what we actually want to do, which is develop algorithms using spectral data to estimate water quality and comparing them, doing the calibration and validation exercises. And, I'm the bottom part. I want the processed imagery to create water product products that goes into my processes. And oftentimes things don't get there because, the papers kind of stop at that blue part in a lot of cases. When you work in an environment like Earth Engine, that upfront cost is minimized. You spend more time working on the stuff you want to, doing the science, and ultimately, hopefully, have time and energy to do the last part, which is creating the products that people would use for their own purposes. And an advantage of having all of the work already on the internet, on the servers, is that you're a closer step towards sharing it and producing it. So that's the big picture, and now I'm going to go small picture. The first algorithm that was chosen by the work group at the beginning was to implement a TSS algorithm called SOLID, and our goal was to implement it in an Earth Engine environment. And we've been doing that since that task was sent out, and sort of the people working on the nuts and bolts, Kelly, me, and Saba Bora from the World Bank, have been working in a GitHub account that's linked here in a Google Colab Python notebook style. So if you've worked in Earth Engine before, you can work on it through a JavaScript API or JavaScript environment, or a Python API through either local Python or through a notebook. And we are first focusing on using Sentinel-2, assuming post-atmospheric correction. So I'm explaining the TSS part, but a big effort was figuring out which atmospheric correction would be the right one to put at the beginning of this process. And so Ben and Kelly will talk about that. And what we did pretty quickly, and when I say we, I mean Saba did very quickly, was built a process that went from taking the data from Earth Engine, bringing it into the Colab notebook environment. I call that local because, in a sense, we're not leaving it on the Earth Engine part of the servers. Now we're essentially doing what I would consider quasi-local work, and running the SOLID algorithm from the Python libraries that already exist for the project. So there's a great GitHub linked with that paper at the very bottom that lets you run the SOLID algorithm from Python libraries. And then we take the results of that, we put it back into Earth Engine for visualization purposes. So that's good in the sense of like bottom right image, we can give it an image number, create the TSS estimates, and then display it in Earth Engine. But that's not really what we mean when we say in Earth Engine to take advantage of the scalability of that platform. In order to do that, you have to take the nuts and bolts of that solid algorithm and get it in the language that Earth Engine uses to run its functions. And they call that for a machine learning model, it might be they call it EEification, or moving it from where it is into being able to be called by Earth Engine. And so if you're familiar with the solid algorithm, which I wasn't when I went right into it, it's really 3 processes put together with some logic on which one to run on which water type. So that image on the top right is showing the band logic and what algorithm you might run. So 1, 2, or 3. 1 is a QAA analytical algorithm to get to total suspended solids. 2 is a neural net model that was fit in Keras TensorFlow package. And then 3 is another analytical model. So 1 and 3 are pretty straightforward, and what we did first, rescript the processes with the functions for Earth Engine to do the basic math to make that happen. The neural net model was a little trickier. The goal for us has been to take that fit model from the solid GitHub library, move it to Google Cloud, and be able to call it as part of this process, the solid process, so that all of the work would be done in Earth Engine, and not in a sense of people wanting to use it have to set up their own environment to do it. And this is precisely where we've hit a paywall. So that's one of the downsides of Earth Engine here, is for this type of custom model fit outside of the standard stats machine learning options within Earth Engine. You hit a hosting a model on a cloud paywall, and so we've got a basic one working, and we're thinking through how's the best way now that we have the pieces together. What's the best way to allow people to use this without running up cloud fees, and maybe a combination of asking for credits as a nonprofit versus allowing people to set up their own version and decide to run it. And so we're sort of right there. So that was a narrative way of catching you all up to where we are. We're exploring the in-betweens from purely in Earth Engine to purely local or outside of it, by potentially pre-processing a bunch of image collections using a different resources, and then hosting those. So that would be equivalent to like pre-running these things and allowing you to call them up in Earth Engine. But it's really we're exploring how best to achieve our goals, with the fact that one of the 3 pieces of this model is a sort of a tricky to run at a big scale for anybody, given the fact that you start to run up the tab. There's a little work to make sure we rescaled the bands before and after the Keras model correctly, and that's part of the reason why Saba built that run it from the Python libraries first, is so we'll have something to check to make sure we did it right when we translated it into Earth Engine. And so I want to share where this project lives, so that if you're interested in seeing what we did, if there's parts of this that are helpful for your work, or if you are really good at this and want to help, how you would do that. So I'm quickly going to show you where that library lands, and then I will hand this off to Ben. So let me first show you. All right, so if you want to play along or help, we are within this Google Earth Engine community parent project, and we are GEOAquaWatch water quality. And you'll see here there's a README explaining our goals, the contents so far, how you might contribute if you have the skills and time and want to help us, right there. And within here are the atmospheric corrections that we're working on, and this solid, our implementation of solid in Earth Engine and with Earth Engine in sort of a notebook style. So please feel free to follow us and help us if you have the ability. I'm going to go back to the meeting. that's all I have on the startup and the update on where this TSS work is, and I will hand it off to Ben to follow up.
Okay, thanks, Nate. While we're doing this handoff, is there any quick questions? You can unmute yourself and go ahead and ask them, or type it in the chat. We're not going to spend a lot of time here. Guess hearing none, I'll go ahead and turn it over to Ben.
Hello, can you hear me?
Yep.
All right, well, hello, good morning, afternoon, everyone. Yeah, so I'll just continue on with my segment here. Yeah, so this, for the past sort of 5 years, I've sort of taken on the interest of implementing aquatic-based atmospheric correction for specifically Landsat and Sentinel-2 and Google Earth Engine. I'm a remote sensing scientist, by the way, for Earth Space Technology Services. I'm a contractor to the Earth Resources Observation and Science Center. And I would just like to give a little background on what's going on here. So as most of us probably know, that Google Earth Engine is a front-end web application or API providing access to publicly available satellite image collections from the NASA USGS LP DAC and ESA Copernicus archives, including Landsat 8, Landsat 9, Sentinel-2, multispectral imager, and many, many more. But for this particular talk, I'm mostly just focusing on Landsat and Sentinel-2. Now, OLI and MSI have been shown the potential to map inland and coastal nearshore surface waters with respect to water quality, water color, IOPs, AOPs, etc. And this is a great summary of this has been written by Dr. Nima Palavan from NASA Goddard Space Flight Center on the implications of Sentinel-2 and long-term monitoring of aquatic systems using medium to high resolution satellite sensors. And since the launch of Landsat 8, there's been multiple atmospheric corrections for aquatic targets, and now we're just reaching over or just about a decade of research in that field. And I'm sure most of us, or some of you, are familiar with the ASICS atmospheric correction intercomparison exercise that sort of summarizes all these different atmospheric corrections and provides sort of a performance evaluation for all these different individual algorithms. None of this is available on Google Earth Engine, obviously, because, as I said before, Earth Engine usually just ingests operational products directly from those NASA and ESA archives. And so for an individual, it's sort of rather cumbersome to try to gather all these different algorithms in one spot and run them efficiently. So Earth Engine has the surface reflectance products from OLI and MSI, these level 2 products, and that's great. But however, it does lack that water leaving reflectance property, and which is necessary for these semi-analytical and empirical biooptical investigations that attempt to characterize all these water quality constituents just below the water surface. And so what do we mean by aquatic-based atmospheric correction in Google Earth Engine? Simply just taking the decades of ocean color research and translating all these different ocean color techniques into the Earth Engine JavaScript API. And mainly we're just really interested in this water leaving radiance component, and we do this by isolating it from the rest of the TOA radiances from all the other contributions in the atmosphere and scattering and absorbing molecules just below the surface. So we're mostly just kind of interested to make it in the simplest form, the radiance contribution due to Rayleigh scattering and the aerosol correction, as well as the two-way diffuse transmittance. And so I'm not going to go over a bunch of, like this in great detail, but essentially we're taking Gordon and Wang's approach to Rayleigh correction by defining Rayleigh optical thickness, Rayleigh scattering phase function, and using the metadata sun sensor geometry properties available in the metadata from both of these sensors. In terms of aerosol correction, we're assuming the negligible water leaving radiance in the Rayleigh corrected shortwave infrared bands, where aerosol type is characterized for each pixel from the differences in the two sphere bands. These approaches can be found recently, specifically in Van Helmont, Riverdale, Hugh et al. 2000, and Dash specifically. And so on the bottom right there is just sort of what we're after in its simplest form, where the water leaving radiance is the Rayleigh corrected, or the contributions from the Rayleigh minus the contributions from aerosol divided by the diffuse transmittance. So like Nate had said before, how to access this, the Python script for L8 and L9 now, and Sentinel-2 can be found on the GeoAquaWatch GitHub website. Thank you, Kelly, for translating the original JavaScript code into Python. That was a great milestone, I think. If you want to work with the JavaScript within the JavaScript API directly, we have that too. So really quickly on how to run this thing, you have some options. So for the Landsat portion, you can run it by the WRS2 path and row. And for the Sentinel-2 side of things, you can run it by the tile ID. You can run single scenes or entire image collections. However, that does come with some memory limitations, but you can definitely run statewide or even regional collections consisting of over like 100 or 200 scenes. You can define your temporal regions if you just wanted to look for a specific time window, or you just wanted to look at a specific month for each year, so like just looking at seasonal patterns. And one thing that's really different here is taking advantage of the Google Earth Engine environment is all the other useful climatological auxiliary layers available, such as various forms of DEMs at different resolutions, different ozone inputs and water vapor, CO2, and a lot more. Some things we haven't even experimented with that could even improve, atmospheric correction within this environment. So if I have a quick example, I don't know if I can. Let's see. Oops. Oh, here we go. So just a quick example. If it's just running a Landsat 8 scene over a popular Clear Lake, California. So just between, for example, January and December 2013 to 2021, clear imagery only, we have 39 Landsat scenes. This particular one is from October 16, 2013. And some functions that are useful in Earth Engine is sort of like being able to sort of visualize these things on demand, sort of getting an idea of what the green band looks like for each one of those 39 scenes, or looking at the time series for a few pixels that you're interested in, or even the spectral profile. So it's these sort of tools in Earth Engine that you can get your image, you can process it, and you can immediately look at spectra and time series using that same approach. I don't know if I'm on the right screen. Is this right? Yeah. Yes. Some of the advantages of GE, like I said, it's accessible, open access. It's accessible for the government, academic, commercial, and personal use. This will allow for vigorous testing of the performance of MSI and OLI RS algorithm development across global regions and scales. The several auxiliary data sets to help inform atmospheric conditions for your target area. In terms of water quality monitoring, it has the potential for seamless integration into lake and coastal management practices, as well as providing sort of an extension for ground-based measurements for inaccessible or difficult to reach locations. And for educational purposes. So I like to show, sort of what you can do in GEE just as a demonstration for the scale of the data you can work with. This is just looking at Texas lakes across the state, summer averages of water clarity, and this was done using a method that published back in 2019. Similarly, Earth Engine has these interesting apps that we can create. So for example, running the same atmosphere correction algorithm using this water clarity index, we can let me try to share this real quick, I'm sorry. Yeah, so this is like an app based on the algorithm that just demonstrated, and showing monthly averages of water clarity for all the lakes greater than 10 hectares for different years. So this isn't obviously verified with AeroNet or in situ data or anything like that, but it is a first step approach using the sort of theoretical literature-based formulation approaches. And what we do get from the spectral profiles that I showed, and just from experimenting in other areas, we do get realistic, RRS spectral shape and magnitude, but it's more just for independent verification now. Let me just switch back here. So in summary, we do have a ready-to-use aquatic-based atmosphere correction script available in GEE for Landsat 8, 9, and Sentinel-2 in both Python and JavaScript. It's available at the GEOAquaWatch GitHub. Performance evaluation and modifications are highly recommended for your study region if you're going to use this. As I said, the spectra, the RF spectra, are not globally verified in situ, so there is going to be a need towards increased verification efforts. This is a temporary solution, I see, until sort of these more operational products become available. Both the USGS, NASA, and ESA are working on sort of their standardized approach to aquatic reflectance, and I know that they'll be having, they'll be releasing them in the coming years. And there's always that future potential for GE to ingest those products once they do become operational. So questions, feedback, and collaboration are extremely encouraged. I'm happy to provide any tutorial. I can be your help desk, if you will. I'd like you to criticize, everything about it in order to drive the science forward, and suggest improvements. Participate in the GitHub repository. Feel free to chime in and share your thoughts and concerns, and that's about all I have.
Okay,
Thanks,
Ben. Thank you. There's one question. I'm not sure if this was directed to you or to Nate. Where can I get access to the JavaScript API version? I see Nate has responded here now.
I'm guessing they're asking Ben where the JavaScript version of the atmospheric corrections live.
They currently do not live on the GitHub, but I will put them up after this.
Okay, good. Any other quick questions for Ben? If not, we'll move on to Kelly.
Bear with me just a moment. I have to share with Kelly. Sorry.
Sure.
Okay. Kelly, you should have the control now.
Yeah, I see that. All right, let me get that into slideshow. All right, I think
Perfect. Thank you.
perfect. No, thank you. All right, thanks, Nate and Ben. You both are awesome. I've really learned a lot just talking with you and working with you on this work. And I thought I should kind of end this out before we go into discussion, kind of stepping back to think about more or less the landscape of working in aquatic um, water quality space in GEE and outlining some broader challenges and kind of where things sit. So when I kind of think about grouping things from our discussions, um, I think one of the first things I think about is data set availability, what is already within GEE. If you look across traditional ocean color sensors like Modus Aqua to more modern ones, Sentinel-G, and then within Landsat 8, Sentinel-2, they are varying products that are currently available, which then kind of naturally lends itself to thinking about, for some systems, you might have a ready-tuned model for your region that can go to an RRS or a chlorophyll product or a water leaving radiance. But for others, you need to implement something like bends to even start unpacking um, what the signals are in that area. Or if you wanted more precision on what's happening with the atmospheric correction, you might actually want to make an adjacent shell script so you can run Acolyte or CDAS. And then that kind of naturally leads into computational languages of comfort. What is the most efficient process to accomplish those things? So what I kind of want to do is kind of walk through those bubbles and kind of see how things sit within that. So just thinking about data set availability. All right. Yeah. If you wanted a classical RRS Modus Aqua product, the level 3 OBDAC version already exists on Google Earth Engine. And maybe for your region of interest, RRS is perfect. You can survive with a 4 kilometer pixel just to do exploratory work. So you could do that right now, and you could even get chlorophyll A. So that's good to know, but maybe you can't afford that spatial resolution. Then maybe Olchi is more interesting, but it's kind of important to realize that what's currently available is top of atmosphere radiance at this point. And while the band designations, like the description is more related to why the band was designated that way, just kind of remember that to maybe for your level of investigation in your area, you need to go to water leaving radiance or RS. So that's something to think about. And then kind of what was brought up before with Ben and Nate to varying degrees is that this is what's available right now in GE, top of atmosphere surface reflectance. There are many studies that have made surface reflectance relations with chlorophyll and other ways, kind of just dependent on what available in situ data you have. But this kind of all points to when we're thinking about larger scalability, there is this need, because there are 3 different variables across different sensors. And this is an older figure, but it's kind of one of my favorites to think about all of the processes that can happen. And if you're more interested in seagrass water column properties, or maybe like the sea surface or surface reflectance, things that are floating is sufficient. Essentially, there's already so much information on GE, but making these individual decisions on your next steps, it can kind of be a lot in working in the GE space. That's why I've really enjoyed being able to meet in this Google Earth Engine GEOAquaWatch working group to kind of tease out like what is the region I'm interested, what's available, and essentially what code can help me explore what is the next step that's necessary in this like processing pathway. And then I'm already showing my bias that I work more with RRS, but there is no RRS or normalized water leaving radiance for higher spatial resolution. And I know for a good chunk of people that might be your interest here, looking at inland coastal areas where it requires um, that particular product. So that kind of leads next into like if I was to make an atmospheric correction pathway on like what exists in GE, you could go down the JavaScript route, which is what Ben presented. When I say analytical, in this case, I'm kind of just like purely equation based, where you're not running Keras or some other learning package in the background. Like this is possible like right now. And then we'll put up a link to the JavaScript version. And then it's the same with the Python side. So what was shown earlier is the main, I call it the main method. That's available in Landsat 8 and Landsat 9. But there's also another option in which maybe you want to use this scalability and just the kind of sheer planetary scale image repository that is Google Earth Engine to just filter out images that you don't even need. What you can do is you can essentially use a Jupyter notebook, filter out a collection, print out functional images for your region, and then kind of use that list to do whatever downloads you need. And I'm not sure if this is, I had this up earlier on our GE. I couldn't find it. I will re-upload this, but that's exactly what I have. We have a script up there that did, or maybe it's still up there, that kind of shows like, maybe you're just looking for a specific scene. And this is kind of one where I kind of walk through like, okay, I'm gonna look for that same image that Nate was working with. I kind of just want to visualize it, see if there are any other images that occurred around that same time. So that kind of shows how to do that. And then I wrote like another box of being like, oh, well, like maybe I just want to run Acolyte from the same Jupyter notebook. And because you can use bash or shell scripts within Jupyter notebook, you can kind of call it. So everything's kind of in one place. That's not going to be efficient for everyone. It's really not efficient for me in particular due to it being taxing on local computing, and that it creates a netcdf and you have to do conversions to geotiff. But that's a pathway if kind of maybe all you just need is to process one image. So that already exists as a Jupyter notebook. And then this was highlighted by Ben about the Python code that exists. And I need to update the GitHub, but I'm starting to throw in water quality algorithms or I've started to put them on to that Jupyter notebook. So there's a kind of a quick chlorophyll C3 algorithm that I wrote that can be added to that. I got it in chat, I think it's 2009. The turbidity algorithm that uses water leaving radiance. So like a part of this group is me getting the inspiration to continually add those algorithms into that Jupyter notebook to be more useful to the broader community. So if we just kind of going back to takeaways, I kind of showed a lot of different pathways to work within GEE depending on your interests. And that right now, like using Ben's method in particular, you can generate RRS normalized or water leaving radiance on the cloud or in a computing platform that's not as taxing on your local system, which can be of huge benefit, especially if, I don't know, like for me, like if I'm switching institutions, it's actually really hard to switch all of my computing resources or the way I did something at a previous institution. So it's really nice to have this kind of place, especially for more exploratory work. And I really was going to talk about this, but the Midwest glacial work, but I kind of wanted to make sure there kind of set the stage of what exists and available. And when we go into the discussion, thinking about kind of adding on, and to Ben's point, criticizing, taking a closer eye to some of this work so that we are putting out really useful things into the community. And for me, one of those things is kind of creating more of these example water quality Jupyter Notebook, Google Earth Engine data sets. just because I've learned so much just on how to look at a region based on Ben's code or code that somebody wrote in another region. All right. So I think I'm gonna get maybe Nate. Did you want to share these lessons learned before we go back into the?
Yeah, I wrote these, so I suppose I should. And people can throw more in there. Um, the lessons we learned, I think one of them is implementation of the machine learning parts of these is tricky, and you run into the coin slot on the cloud computing environment unless you use some of the I'll call them canned, but the ones that are already sort of pre-built into Earth Engine's libraries, which I think is the Smile set, which is like basic. It's like random forests and regressions and a lot of things that probably are good enough, but it's not the thing you would need to like, okay, take this really custom solid neural net thing and make it work. So that was a lesson. Um, Notebooks have been a decent way to collaborate and share. It is another, besides the JavaScript environment, it's another way that we don't have to set up, the same systems and be really careful about our own personal computing. You can have it all done for you, so we spend less time on like, which libraries did you install and did you do this right or that right? Instead, you can talk about the stuff that really matters. And then I would throw in the benefits of working relationship. So not just talking in theory about these things, but getting into the nuts and bolts together has been really good for me because I learn from Ben, some things that he's overcome with some of the atmospheric correction. I learned from Kelly about issues with a QAA algorithm I was working on in coastal waters, and being able to work on something tangible has been a real benefit to getting to know each other and learning from each other, as opposed to just sort of vaguely knowing we work on the same thing. If we work on some actual problems, it's been nice. So those were my takeaways so far. Others are welcome to jump in.
Hey Ben, did you want to say any last takeaways before we kind of transition to Q&A and those discussion questions?
I don't think so. No.
This is Steve. I would just want to conclude this portion of the webinar and say, I've really been appreciative of all the work that the three of you have done. It's amazing stuff. I think, this is one of the tenets or the reasons for AquaWatch is to bring this community together and to provide a home, if you will, or a space to, for people of like minds to get together and learn from each other. So this project and this working group is an excellent example of that. And again, hats off to the three of you and your amazing work you've done on this. And with that, I'll turn it back to Kelly, who now is going to, I guess, lead some of the discussion and facilitate the work going forward.
Awesome. Thanks, Stephen. Thank you to Steve for bringing us together and creating the space and the drive. Yeah, so I think we really wanted to listen to your questions, but also experiences working with GE. And I put these discussion questions up, but it's kind of, this is more of just some time that we wanted to dedicate to kind of hearing your thoughts, what could be improved. And I know going around the room with 40 something people in 15 minutes is not exactly practical. So I put up a link here that goes to a Google form with these same questions that you can actually respond there if you don't get a chance, or if you kind of just prefer to fill out a form basically. And then also in that form, if you want more emails about this group or how you'd like to be more involved, there's a section where just add your email, and then I will add you to the email list. All right, so I think we can open this up to questions or thoughts from people around. Thanks, Nate.
Got a shy group.
So
Give you a hand up.
I do. I was just going to say that. So I work. Uh, Only one of my hats is here with GeoAquaWatch. The other hat that I wear is in the NOAA realm, and there's quite a lot of interest in using Google Earth Engine for processing over there in the NOAA realm, specifically some NOAA Coast Watch products. And I wondered if there was any information that you could share about maybe the benefit of using the because I know you use both merged products as well as standalone products. Were there any sorts of pros and cons to either based upon your experience with the turbidity effort?
You need merged as in like multiple sensors to
Yes, I'm sorry.
endpoint. I mean, yeah. So uh, I can speak to my effort to do that with Landsat and Sentinel for water clarity in coastal waters in New England, using actually a process that Kelly put together in one of her grad work, I think. Um, for us, it didn't matter a whole lot, just because the Sentinel instrument came around so much more often. It fit our need, and adding the Landsat in didn't really help us much. And it took you have to hold your nose on quite a lot of like band conversions and things like that. So for us it wasn't super helpful. I could imagine for we weren't trying to make like daily estimates of water clarity. It really comes down to end product design and what you would need to get there. For us, we were looking at seasonal kind of climatological things, and it was good enough. So I think a big part of answering those questions is working backwards from the specs of the end product that would be needed. Like for NOAA, hey, we really need daily something, or we really want weekly this, would send us in different directions. The good news with Earth Engine is once you code it up for one image in one day, it's sort of trivial to then do it for all the images on all the days, versus it's not trivial if you've done it all on your own desktop.
Thank you.
All right, I do see Emma's hand is up, but I wanted to check in with Shelly's question. Or just kind of pointed that there for someone completely new to GE, are there any plans from this group on a training session on how to get started in using it for water quality applications? I know Mary responded. Mary, you're specifically talking about what Google Earth provides as the training, right? And not specifically this group.
Yes. Yeah. My comment was specifically sort of the heavy lifting just to get involved in to like master Google Earth Engine because I think that that's no small um, learning curve for that. But yeah, if people maybe have mastered that, we could talk about maybe um, making an opportunity for more like a hands-on demonstration of what you guys did. If you are amenable to that and others are interested.
Yeah, I would definitely be interested if that's Shelly. I'm not sure if that or where specifically your kind of question sat. Okay, great. Can you post a link to the beginning class? Okay.
Yeah, so just to elaborate, I'm a basic remote sensing, we've written scripts to process satellite imagery, have not worked in the cloud at all. So like I wouldn't even know where to get started. And I'm a Coastwatch node manager, so this would be within the realm of, how would we use it for Coastwatch applications and mostly coastal issues, algal blooms and water quality sort of applications. So yeah, where would you start? With maybe the Google Earth Engine class or looking through the scripts on your site to start with? And it sounds like probably both. But yeah, that's basically where I'm coming from anyway, is familiar with remote sensing and working with imagery, but how do you then move towards using Google Earth Engine?
Yeah, I could speak from my experience doing that same thing of like, how do I make this work? And I did attend some of the in-person Earth Engine trainings that were more general about the platform. Those are all on YouTube, and they're also those examples are also on the Earth Engine documentation, and they're really good with links to like running scripts. So following along those was my start. Given that we've done a lot of that for water quality applications, I think you're right. We may be in a point like there's another collaborator, Tyler Erickson, who's a Google development advocate, I think is his title, and maybe some combination of like basic training and then like the example we use is like Kelly's Landsat 8 to water clarity or something like that. A combined thing could work really nicely if people wanted. I think that's a good idea. Having like a training script or something that gives you the basic moves. There's only so many moves, and then it's variations off of those that I found. The biggest thing for me, with some coding background, but without enough topical knowledge, has been having the examples of the things that Kelly and Ben wrote to modify off of.
Yeah, and I think to add to Nate's, I think what I found the existing tutorials on Google Earth Engine, there aren't that many like water quality applications from traditional, I would say like ocean color sensors. So I know for me, that's at least where I I struggled with a bit, like some familiarity with programming, but I think that's why this group for me was like really important to see like, all right, am I just not aware of certain code or scripts that exist? And like, fortunately, like through this group, I was able to find like some people have code on how to do things already. Um, so yeah, I do think there's kind of like a two-pronged approach you could go if you're like just approaching this. Like you can learn a lot about just like GEE code writing from the tutorials that exist, but also there's the you can kind of look at this one to see like, all right, I learned how to write this code and from whatever GE script that exists, like how would I adapt it with like more familiar like VR sensors or whatever it may be.
And if you're looking just to get past all that and just trying to get to what you need to get to, kind of like how Nate was talking about, he's a user of the data. He doesn't want to spend all this time learning and all this. I mean, don't get me wrong, I'm not learning, but there's a lot of hurdles for us, for researchers, to, in order to get the answer they want. So just email me. Like, happy to help.
Totally agree with Ben there. Please email us. I'll put our emails in. All right, we'll go to the chat. Emma?
Hi, can you hear me?
Yeah, we can hear you.
Yeah, I just had a question about how much, or if you could say a bit more about whether you have experience with using the user interface tools to make apps in Earth Engine, because I think that's one thing I've found really useful in using Earth Engine is the fact that you can make apps available so that people who don't have a remote sensing background can then use the data sets that you produced. So yeah, have you had much experience of that, and have you had any feedback from users about how useful they found those?
Yeah, I was gonna say Ben or Nate. You both have really great experience.
So I've used the app functionality for not for public consumption, but for like work groups. So our EPA people that are working on something to be able to display it and click through a image collection and scroll around. I would say I put a link in the chat which has a bunch of examples of apps other people have built that are far more polished and useful than the stuff I have. And mostly what I've done is because those are built in the JavaScript environment, you can get a link to the code that creates them and you can see how the UI scripting works and take pieces and parts. As not a front-end developer, I found that challenging. I think it's a somewhat specific skill, sort of the JavaScript I guess widget building that creates them. However, there's a lot of templates now from other things. Like I used like someone had done like an NDVI forest displayer with a color bar, and I was like, well, I want to do that with water clarity, so I just sort of brought it over. You run into all the little, data type coding errors and things that you have to work through. There's no avoiding that. Like, there's never like a one-to-one script porting ability, but it definitely gets you really close to your goal. And even me, who's not a JavaScript expert, can get to the point of sharing something with a animate tab and a water clarity bar and even an export button. So I highly suggest looking at some of those examples on the Earth Engine app. And there's also ones where you can see the underlying scripts from other people's projects there too. Dream world, right? Something like this we have different sections on the GitHub. We have atmospheric corrections, water quality algorithms. It'd be really cool if we have a user interface catalog of things that applied to aquatic remote sensing, and maybe even a calibration validation folder. That's a dream someday to have some examples of those together. I would say I don't have real good ones. Ben might have better ones than me at this point.
Kelly?
Oh, I was gonna see if Ben was gonna
Oh, okay.
Ben, did you want to say anything? Because I know
No, I was
you
just
work a lot with the JavaScript environment.
no, yeah, just to back up on what Nate said. It does take a different sort of skill set for the front end apps. I only have a little basic understanding of it, but yeah, just
Awesome.
echoing what Nate said.
And yeah, Emma, we definitely are happy to invite you. It sounds like you've had some experience with those apps, and we'd love to hear more from you.
Yeah, I don't have tons of experience, but I found there was some good YouTube videos that I've followed that were really helpful for that. So yeah, I can send some examples.
Thank you. All right. I see. I know we're getting kind of close to the hour, so if you have to hop off, understand. But I can still stay on to kind of keep discussing things. I'm not sure about everybody else that just presented, but we can stay a little more. Our second question from apologies, Chue. Did I pronounce? I'm not sure if I pronounced that correctly. But...
Hi, can you hear me, Kelly?
Yeah, we can hear you.
Okay, yes, tree is correct. So it's like a plant. So I'm from Canada actually. So I'm in environment in change Canada, and so we are interested in using the GE for some long-term lake water quality monitoring. So I last about a few months ago, I tried once using GE to build some like a 2 decade long time series. For example, for Lake Erie or some other lakes, we eventually will want all the lakes in Canada, about 500 lakes, using the Google Earth engine for some very quick analysis and also some visualization. However, what I noticed is I'm not an expert on GE. I never used GE before, like last year, and then I just started this summer, and then I took a few months. I also follow those APIs and some tutorials. And then I basically come out to two approaches to using the GE. One is using the JavaScript to actually, like some basic way to do it. Another way is using a virtual machine actually on the Google Cloud platform. And they're using some virtual machine inside. And from there, I can using GE more like an API approach. And that's actually the way I go in later because we need a little more advanced analysis. So that's the reason I use that approach. However, then my question is, I noticed there's a lot of issues with the data itself. For example, like as you know, you also mentioned about OCHI. When I'm working on OCHI data, I noticed a key band we are working on, which is 709 nanometer, and it's always a negative value. I don't know whether you get a chance to look into it, but I notice it's always negative. So I opened a few tickets to their Google Earth engine, like issue tracker, but I didn't get some answer from them. I don't know whether you guys have any experience with that. So that's basically my first question. Is like I think the second question is very relevant as well. So it's I noticed Google put all those satellite imagery from, let's say, European Space Agency onto the Google Earth engine, but with some resampling. And I noticed the data is not exactly the same anymore compared with our local processing. So that's the reason we cannot get some consistent results compared with our, download the data directly and do some processing. So using Google Earth engine going to introducing some differences. And that differences is mostly because I think Google Earth using some resampling in order to make their product consistent with other, like say Sentinel-2, Sentinel-3, or some other like MODIS data or from Landsat data. They all mosaic together or make them like consistent in order to showing full processing. And do you guys have any experience on at least do the calibration or analyze about what kind of issue is inside or how reliable it is compared with the raw data? And yeah, so that's basically my question. I see some very interesting result you previously presenting about like say turbidity like analysis. I'm also wondering again the calibration, like how reliable is those output? I know you're using some models like MDM from like other groups, but I'm just wondering, is there any like local calculators in order to validate the results and at least give her some accuracy assessment, like at some level? Thanks. I think like all my question altogether is all about calibration or how reliable is the data, and then how reliable is the result. Yeah. Thanks.
Yeah, we call quality assurance. Yeah, go ahead, Ben. You're talking.
I don't know for terms of Sentinel-2, in terms of Landsat, the products ingested into GE is the exact same from LPDAC, so there are no changes or corrections or resampling on that front. I do know Sentinel-2 just reprocessed their entire image collection, and so now if you look, they have a harmonized data set, GEE. If you do not use that, you will see huge differences between 2022 data and the rest of the data. I'm also with you when it comes to bringing up issues on the GE developer forum board. Sometimes, I mean, they're really not there to help you. They're just there to, I really don't know. It's more of a community forum, I would say, rather than those responsible who actually put up the engine. In terms of the in situ verification or calibration, no, because this is sort of our first stab at analytical approaches using cloud computing and traditional ocean color techniques. I would like just to say that like those papers would have resulted in their their algorithms are validated at specific regions, but probably not for your target region or my target region. But that's kind of on us or the community, the aquatic science community, to go out there and sort of test these algorithms and verify them on our own dime, really.
Yeah, I'll jump in on verification. So that was like top of my mind as coming from outside the field, as I see all these different ways to get to this, and there's so many. It's choose your own adventure on almost all of these algorithms and pieces and parts. And as someone who says, I want to get to water clarity, I started from the how well does it do against in situ data question. So for some of the applications, I started doing this. I wrote validation processes to pull in water quality data, compare the two against what's being run, so I could decide, hey, how much of a problem is this surface reflectance versus RRS, starting with RRS for this process for what I'm trying to do. And I'd love to share some of those in this GitHub. Maybe not everyone's interested in my validation to, Narragansett Bay, but there's all those processes of, pulling in a CSV with time-stamped water quality data and then connecting them in time and space with the window is just a common thing we do. And if someone else wanted to do it, they could copy and paste the code and adjust from there. So at least for my use of Earth Engine, I've also used it at the end for some validation as well. This group around the solid was not interested in testing an algorithm and see how it does as much as porting a one that the scientific community agreed on was the right one to go with to a larger scale. So the problems we've been fighting have been make that work. Our first validation was, do we get the same thing as running it locally on the Python library? So forget the actual water quality measurements for now.
Yeah. Also,
Okay,
you mentioned
thank
you
you.
were from Canada, and if you're familiar with Jeff Cardill from McGill, I know he has some excellent literature on Google Earth Engine, remote sensing, aquatic science in Canada, so Canada lakes.
Yes, we do have some cooperation, I think. I mean, pretty casually on some of their related water quality. I know they are using more GE than us. We just start to using those tools. But for us, we would really want the data to be reliable before it really plug into our current data processing system. We have some other resource to do the processing, but we want to take advantage of GE in order to apply the models to nationwide for many lakes. Yeah.
Yeah, and
Thanks.
the changing data inputs is not just a GE issue, right? So like I've been caught in this Sentinel thing upgrading, at the time the Landsat switching to collection 2, like there's no getting around. They're going to futz with the data formats and processing, even from, I guess you'll say the source, unless you're going really, really raw. So Earth Engine gets, I don't think that's a unique problem to doing the processing in Earth Engine. You're going to run into the same thing, even just downloading the images from ESA or USGS.
Okay. Yeah. Thanks. Yeah, I'll send you maybe some. I can even share some of my result if that's useful, or like we have some further discussion. Thank you. Yeah.
Yeah, that would be fantastic. Thank you. I see one more hand up, and then we'll turn over to the chat for Ravi's question. Abhishek?
Hi Kelly, can you hear
I
me?
have Abhishek. Yeah, I can hear you.
Yeah, so I'm Abhishek at UMass Amherst, and I'm working with cyanobacteria remote sensing. So I found it really useful. The code Ben has shared with me, so I'm using his code for especially the Rayleigh corrected code, because the RRS product like seems like sometimes like not working for my work. But what I found most challenging working with cyanobacteria remote sensing is the OCHI data, which is like the you don't find the metadata in the Google Earth Engine. So I was thinking, Kelly, if you have found any solution for that, working with like in the Jupyter notebook, is there a way we can do atmospheric correction for OCHI? Uh,
Yeah. So I'll say I haven't looked too much at the OCHI data, so I'm not familiar
mhm.
at the moment with the how the metadata is presented. But I kind of one of my natural links is that I know that a part of the Acolyte workflow, they do pull some of the metadata from Google Earth Engine. So that's kind of like my only like my thought at this stage is like I don't know, but I do think there is some type of a path. I think it's just kind of more like structuring code. So, but this is like a good project to think about and work on. I don't
Yeah.
know if Ben or Nate has additional thoughts on that.
I haven't tried that instrument for anything for me.
Okay. All right. Yeah, we can talk. We can talk
Yeah,
more.
yeah, no problem.
Yeah.
Yeah.
All right.
Yeah, and also I found like because I don't know if some of you have experienced this or not, downloading Sentinel-2 or Sentinel-3 data from the like scientific data hub. They have put like all the product offline, and it's so difficult to download the data. So in that scenario, I think GE is right now the best option for me. So like it's such a pain to download like all ESA data product. Yeah.
Yeah. Yeah. The Sentinel-3 metadata issues. Yeah. An issue.
All right.
I
Well,
would
thanks,
like to.
Abhishek. Let
Yeah,
chat
thanks,
more.
Kelly. Thanks, Ben. Thanks, Nate.
Yeah. Good to see you, Said. Hear you. Or Abhishek.
Um, I know there's a question, or there was a question in the chat. I just kind of wanted to scrolling up through it now. I'm not sure if Robbie or Ben wanted to speak to that.
Kelly, could you read the question?
Yeah, hold on. I'm trying to find it. Okay, there it is. Don't know if the question is directly related, but I saw salt and pepper effect and Sentinel-2 image at 20-meter resolution while generating a map for the whole lake. Is that a common problem for mapping lakes at high latitude? Do researchers resample at 60 meters for the maps or use any smoothing filter? And also, does your code for atmospheric correction include glint correction? I'm currently not working in, or I work in high latitude systems, but not in GE right now, so I'm actually not super familiar. I'm not sure if Ben or Nate or anybody online can speak to that.
Anyone could correct me if I'm wrong, but yeah, if you're using C2RCC, if they're using the SWIR bands for aerosol correction, that has a lower signal to noise ratio. You're working at high latitudes. I mean, there could be a little more grainy. Not sure if it's like a common problem for mapping lakes at high latitude in general. But yes, the JavaScript script includes a glint correction. It's currently commented out, but you can uncomment it and it'll be implemented. With that, you might get some negative reflectances in the near infrared. Just be careful where. Make sure there's glint.
I haven't uploaded it yet, but I have a QAA water clarity algorithm that has I think it's a really dumbed down glint correction that starts at the top of it. I will make a point to put that up as well.
Yeah, so I mean, discussions like this could branch off another folder, potential glint corrections, right? So now we have two to look at. So
I saw a comment from Rabia, if I'm pronouncing that correctly, doing random forest implementations for water quality parameter prediction. I had a similar instinct to that, especially for like local applications where I'm not like gonna take a random forest and put it in Maine, even though I fit it in Rhode Island. But I think Earth Engine has those more common algorithm fitting techniques that you can run and not hit those paywalls that I find interesting. And then it's just a matter of validation in space and time and stability and things like that. And I think that approach has a lot of promise. We actually thought, okay, when Google took a look at Acolyte, they said, oh my God, this is terrible in terms of how complicated it would be to put together in their environment. But maybe they could just train a random forest to proxy it. Basically build a machine learned version of it and have that be what they use to process the imagery. So I think a lot of people are thinking how to take use of those other functions like that to solve some of these problems. But again, that's all going to start to be approximations of approximations and getting a little further away from some of the remote sensing knowledge that's in these analytical algorithms that, from my experience, do help in transferability in space and time for like trying to get water clarity. Like I fit random forest models in Earth Engine. They work great in sample, and then you go a few years ahead and all of a sudden they don't.
All right. Thank you for that question. I see. Oh, Ben, were you going to say something?
no, looks like Steve has his hand up.
Okay. All right, Steve.
Yeah, thanks. I just wanted to touch on a point that I think, Kelly, you brought up earlier about approaches or directions, and Emma had touched on this also. When we wrote this proposal back in 2020, we were going to build this layer, this kind of reference layer that would be available to the whole community. We were just going to do it. So it's kind of a top-down approach. And we're still working on this, and it takes a lot of computing resources, as we've heard, and we're not sure of its future. And in talking one day, kind of offline with Ben, we talked about another approach being kind of where we would build this front end kind of web service kind of on demand, where you could go to a particular region, pick a time frame, and let Google Earth Engine just do it. That would save on a lot of computing resources instead of doing it for the whole globe. Just do it for your area. And I'm learning both what your thoughts, what some of the other folks in the community here think of these different kind of approaches to. I mean, ultimately, AquaWatch is about providing information in a palatable form for people to use, fit for purpose, as we say. And what's the best way to get there? There's, as you say, there's multiple pathways, but I'm just curious what people's thoughts are on that issue.
I think the idea of letting Earth, zooming in on a region and running it for smaller places makes a lot of sense. Most people want a single lake, set of lakes, state, something like that. It solves some of our problem, but we still hit the paywall, at least in the solid model, the way we're doing it. We could definitely provide notebooks that allow people to run it in their own cloud setup, but that's just it's a little bit better than local, but it's still going to be a lift for people to set up. If we had models that were fit in the standard libraries that are basically free of charge within Earth Engine, we could do what Steve and what you're describing of zooming in someplace or even running it for the whole Earth. So the question becomes like, is it worth switching to attention on those where it'll be simpler, or making this particular one work correctly with its limitation on because of that neural net model?
I think I kind of like mapped out kind of how my brain works with all of these different pathways. But I think like when I think about my longer vision, like what I would love to see is for some of these that don't require any type of neural net learning type of environment. A lot of these algorithms already exist, like that can already be typed up. I mean, when you're thinking about maybe more like optimization based code, if you're, I don't know, if you're, there's a like that, maybe not necessary, but there's like a ton of literature already that exists where you can look at we can look at band ratio algorithm, you can look at all of that, and like those are a kind of in my mind, those are some low hanging fruit that you can get to. And I think I work on converting some of that into the GE environment, and I think it's just like the only thing for me that's been a little bit different, not necessarily a challenge, is that how you do like math expressions or like band math is, I mean, just a little different in the GE environment than outside of it. But I think like my longer vision is that I would hope that these types of algorithms that already the community are familiar with, like we can already access that in GE. Just, I mean, because yeah, I think only in the past, I don't know, maybe 10 years, more, it feels more like 5 years, but I mean, in a PhD and postdoc within that realm, is like utilizing things like deep learning neural nets or whatever. But there's already rich literature, in my opinion, about low-hanging fruit for algorithms that I think already could be implemented, and I think that's what this group can provide.
Right, right. I mean, my question was more of, not algorithm choice, but I mean, how do we make this palatable for a water quality manager whose day is already full and is not going to learn how to do a lot of, is not going to write scripts, is not going to,
Yeah, in some of my
develop.
experience, Steve, it's a lot of water quality managers more interested in the flags. Is it bad today? Or what was it like last week or last month compared to today, or yesterday compared to today? And just looking at time series of the historical Landsat or Sentinel-2, these are systematic observations happening every 3 to 5, 8 days. And if you're running the same algorithm on that data set, you're going to see the lows and the highs, and just visually you can just already tell when there's like getting high reflectance in a particular ratio. That's obviously a bloom or something, or maybe not identifiable of what kind of bloom that is, whether it's suspended solids or cyanobacteria or whatever, but it's definitely more turbid than what it was in my last image, for example. And then people can start making sort of visual inferences or qualitative inferences from that.
Yeah, I would say what you're describing, Steve, is the Earth Engine app, right? So build one where there's no coding required. You log in, you zoom into your place. There's a download button or a time window thing, or you could swipe through the image collection that gets filtered based on where you go and the time you pick. All that's doable in the Earth Engine app, and there's examples of it in different ways. I think that would be the best for the type of user you're describing. If you could kind of limit the dimensions of, it starts to get crazy when you're like, oh, I want to see TSS and clarity and
Yeah.
3 different ways in this,
Sure. I mean, what's kind of sparked this for me, no pun intended, but forest fires. There's a woman on campus here who's using Google Earth Engine to map forest fires, and again, with a similar capabilities that we just talked about, go to a certain area, certain time frame, and boom, it does it, for the forest managers. So that's
Yeah, I do think I think the Jupyter notebook, at least for the one I wrote for with Ben's algorithm, I mean it runs a scene. You can narrow the window. I think the only thing that, at least right now, I haven't wrote the code for is the visualization of, but like right now the code base exists. I think there's that one next step that I think kind of more comes down to like user interface of how you would want something like that designed for you. But that's kind of more from like a Python environment. But I think is already, you can also accomplish that from the JavaScript app version that Ben has.
okay.
Um,
Thanks.
yeah.
storyboarding an app that would work for this group, like a dream app, I think would be starting at the end and working backwards. I think would be a nice next step for that. Let's say TSS and work back like, hey, we want to be able to zoom in anywhere and do TSS at a weekly resolution and have this sort of functionality. And then we could look at each other and say, I can't do that with the solid one, but we could do it with this one, and we, scoping it that way.
Uh, I know we're coming up on the end of the time block. Mary, did you want to let everyone know about the next webinar? If there are
Sure.
any comments from the group.
Right. The next webinar will be presented on January 26th at the same time. Will be presented by Dr. Sam Batsley from the University of Wisconsin. And we think he's going to be demonstrating a version of the Real Earth portal that will be made available through the GeoAquaWatch website. And so we're hoping to learn more about that effort. Steve was also involved in that. So Steve, I don't know if you want to add anything that he might be presenting. I'm hoping to put out the advertisement for that tomorrow. Didn't want to confuse people by putting too much about GeoAquaWatch webinars in your inboxes at the same time while this one was being advertised. So, I'll send that
Yeah.
out.
I'll just quickly say that this is a project that we received a small grant for. On campus here, we have something called Real Earth, and it's a portal of thousands of different data sets. And we decided to bring in some of these kind of disparate data sets in water quality, and be it from satellite derived water quality information, also with in situ um, data, and merge it or be able to bring these together and compare and contrast. Um, and some of these data sets are not very accessible, and so this is one way to quickly get at some of these data sets, such as Copernicus, land products, the climate change initiative, water quality products, etc. So yeah, it's pretty exciting work, and Sam will share that.
Okay. Oh, sorry. Okay. Thank you very much, Steve. And want to take an opportunity to thank all of our presenters, Kelly, Ben, and Nate, for doing a great job. I do not recall if it was pointed out that they're all three early career scientists, but they are. And we have a new early career society within GeoAquaWatch. And if you would like to join, all you have to do is self-identify as an early career scientist and contribute to meetings. I have put my email address in the chat. You can send me an email and I'll get you connected to that early career society. And if you'd like to interact with the presenters a little later, today the recording will be posted on our website, and you can find their email addresses there and interact in the future. So thank you very much for joining today. We hope that you'll also join us on the 26th for Sam's webinar as well. And is there anything else, Ben, Kelly, Nate, Steve, that you want to share before we close?
Not necessarily. Just thank you, everybody, and thank you, Mary Beth and Steve, for having us.
Oh, I think, yeah, I'll just add that we're very grateful, I think, to both Google Earth Engine and Geo for enabling the grant that got us together to start this work. And we're glad finally to be able to share some of those results. So thank you all for working on it.
Yeah, thanks for working on it. I know this is a best effort, so it's nights and weekends, and hats off to you guys for all your time you've put into this.
Okay. Well, thanks everybody. Have a great day and Happy New Year. Bye-bye.
Thank you.
Bye. Thank you.
Bye.